Hello and welcome to another Column Cymru session. My name is Grant Mackenzie and I will be looking at statistics, Poisson model. Okay, so if we look at the next slide, as you can see, we're going to be working with the Poisson distribution and modeling with it. I've tried to make a varied or looked for a varied selection of examples, which I'll be working my way through. On this slide, I will talk to you about the what makes a Poisson distribution and also the formula and how to sort of look up things using either the calculator or using the tables. I would suggest that you are going to have to use all three. If this question has said for you to calculate, or if it's a single event, I would always use the formula. And then if there is a sort of CD, which is the cumulative distribution, then I'd use the white calculator, and or even which is black now. Or I would also then, for the one, there are a couple of questions where you're going to have to use the tables. I have included the tables in those type of questions so that you could see how they would work, but you need to be looking at them. As always with the Column Cymru videos, what I would suggest is maybe let me go through one or two of the questions, then pause it and work your way through yourself. There's not the same questions time and time again. What I have done is I made them as varied as possible, bringing in some pure maths as well. So if we get started, conditions for a Poisson model. There are events occur singly and at random in a given interval of time or space, and are independent. Then the next one, lambda is the mean number of occurrences in the given interval. Okay, so those are the two things. As I said, you always have to relate it back to the question. Examples would be the number of emergency calls received by an ambulance control in an hour. So it's single events because there's only one person that's going to be able to take those calls in. They are random because they're also independent of each other. And you've been given lambda, which is the mean number of times received in that control hour. The other one is the number of vehicles approaching a motorway toll bridge in a 5-minute interval. Again, it's giving you the time frame. It's singly because you can only pass one vehicle through the toll, and it would be specifically giving you the rest of the information. The formula, as I told you before, so if px is equal to n is equal to e to the minus lambda, and then it is lambda to the n over n factorial. Okay, and I would suggest that if it is a single event that you would use this. The calculator itself does calculate these things. However, I've seen in several mark schemes that if it is said calculation, it's expected to see it, otherwise you won't pick up any of the marks. The calculator that you would use, I mean, this is the one, and it's out of frame, but this is the sort of the white calculator that I've got, which I won't bother trying to sort of show you. And it would be menu 7, and then you've got the two different types. You've got the Poisson, and then is the PD, which is the very specific probability distribution, or it is CD, which is the cumulative distribution. On top of that as well, you have a list of tables in the booklet that's been given to you during the exam. I would highly recommend them. We are going to, I think there's 4 out of the potential 11 questions that you are going to have to use the tables, or it's going to be the calculator, and then it will be looking at individual points. It's a lot difficult to see with the calculator because it's going to be trial and improvement. So as I said, I would highly recommend having the tables out in front of you for this as well. Okay, on to the first question. So the first question is: a study undertaken by Good Health Hospital found that the number of patients each month, X, contracting a particular superbug can be modeled by a Poisson distribution with a mean of 1.5. So that 1.5 is the number of patients that contract this particular superbug. So we have been asked to work out, calculate px equal to 2. It's very much calculation. So we are saying that it's always good to sort of put x belongs to the Poisson of 1.5. And then the first question, as I said, is a part 1. What's the probability that x is equal to 2? So using the formula that I sort of stated earlier, we have e to the minus 1.5 1.5 squared over 2 factorial, and that would give us then an answer of 0.251. Part 2 of A, hence determine the probability that exactly 2 patients will contract this superbug in each of 3 consecutive months. So as I said at the beginning, this is per month. So we already know that the probability that 2 patients contract it in a month is 0.251. So then to have it in 3 consecutive months would be 0 probability of 3 consecutive months is going to be our previous answer of 0.251 cubed, because it's just going to be 0.251 times 0.251 times 0.251, which is going to give me 0.0158. That's the first question for 4 marks. Part B, which I'll put here, is write down the distribution of y, the number of patients contracting this superbug in a 6-month period. So we know that there is 1.5 patients per month. So now what we have to do is we have to change it into a 6-month period. So it's going to be 1.5 times 6, which is equal to 9. So our new distribution y belongs to the Poisson, but this time lambda has changed from being 1.5 to 9. And then part 2, it is find the probability that at least 12 patients will contract this superbug during this given 6-month period. So if we say that the probability that, what do we want, at least 12, so y must be greater than or equal to 12. Now this is where I wouldn't use sort of the statement of the calculation, because of the fact that you're going to have to do for x equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So here they would expect you to use tables, because to calculate this is going to be 1 minus the probability that y is less than or equal to 11. This is a case of looking up on the tables or putting in the calculator, and have 1 minus 0.803, which is equal to 0. For some reason I forgot to calculate these. 1 minus 0.197. And then part C, state 2 assumptions that implied by the use of the Poisson model for the number of patients contracting this superbug. So the assumptions, again, we need it related back to the question. So it would be attacks for the first one, attacks patients randomly, attacks patients randomly. And the other one would be attacks patient independent of others. Attacks patients independent or independently. So those would be the 2 that you say. Although if you said singly, it doesn't really make sense in the context of this question. So you always put it in the context of the question. Moving on to the next one. So here we have in a peat bog, a spotted orchid occurs at a mean rate of 4.5 per meter squared. Given assumption not already stated, that is required for the number of common spotted orchids per meter squared of the peat bog to allow a Poisson distribution. And again, this is context of the question. So part A, common spotted orchids occur randomly or independent of each other, or independently would be probably better. So either of those would be perfect. And then given that the number of common spotted orchids in 1 meter squared of the peat bog can be modeled by the Poisson distribution. So here now is where we pick up the 4 main marks for this question. So if I put part B here, so find the probability that a random selected 1 meter squared of peat bog there is exactly 6 common spotted orchids. So again, I would expect the calculation, so px equal to 6 for, and I should have stated this before, x belonging to the Poisson distribution of lambda, which is 4.5. So then this is e to the minus 4.5 times 4.5 to the power of 6 over 6 factorial. And then this would give us 0.1281. That's part 1. Part 2, there are fewer than 10 but more than 4 common spotted orchids. So the probability that, so there are fewer than 10 but more than 4, so 4x10, which would then be px less than or equal to 9 minus px less than or equal to 4. And again, I would expect you to be able to pick these up either on the tables or in using lambda equal to 4.5 or using a calculator. So it'd be 0.9829 minus 0.5321, which gives us 0.4508. And that's that question done. As I said, if you are finding, they do alter and are more varied, but if you are, the reason why I put this one is because of the fact it's between 4 and 10, and I wanted to sort of showcase that. And the next one, there'll be a slight change. The first couple of parts of the question are going to be the same, but then there are going to be a third part where you have to change things slightly. I would, if you're finding this bit a little bit easier, pause it, do it yourself, and then you can sort of buzz forward and then you can make sure you get the right answers. Okay, next one. Here, the number of particles per millimeter in a solution is modeled by a Poisson distribution with mean 0.15. So that's particles per milliliter. So a randomly selected 50 milliliter sample of the solution is taken. Again, the reason why I want to show this one is because they've given you the sort of the mean in the statement for the first part, and then for the second part, they have changed it, and you need to be aware that you have to change it yourself. So if you'd have put the lambda as 0.15, then you would have got the full question wrong. So it's important that you read what it's asking you to do and then put it in. So here it is part 4, so I can get the calculations. So here we need to find the value of lambda before we can start. So it is 0.15 per milliliter. We have 50 of them, so we're going to do 0.15 times 50, which is going to give us 7.5. So now we can say that x belongs to the Poisson at 7.5. And then we just go about our business to work out the question. Exactly, so again, find the probability, exactly 10 particles are found. So for part 1, once we stated at the top, we would then say px equal to 10 is e to the minus 7.5 times 7.5 to the power of 10 over 10 factorial. Remembering 10 factorial means 10 times 9 times 8 times 7 times 6 times 5, so on and so on, and it is the button on the calculator, and that is equal to 0.0858. Part 2, between 6 and 11 particles inclusively, that part is there. So because it's inclusive, we would say that P is 11x6. So that would mean then we are going to do Px 11 minus Px5. So we want to include the 11 but exclude, obviously because we're including the 6, we wouldn't put the 6 there, we're putting the 5 there. Those values you'd look up on the tables or on the calculator, and it's 0.9208 minus 0.2414, which is 0.6794. That answers your question. Nice 5 marks or 4 marks, and then move on. And again, if they ask you to relate it to the question, what does this mean? Then just make sure that you are sort of putting what it is asking, which is the particles per milliliter. Next question. Notice here I have added the table, or at least partial of the table, where lambda is equal to 6, and I've given the values for that. I can realize my head's in the way, but it is at the place where I don't need to sort of worry about it. So here we have wrong one. Question 5 and 6 would be sort of similar examples again. So if you watch what I do with question 5 and then you sort of pause 6 to have a go at, you will see what I mean when I sort of change things up. So a number of cars entering a safari park per 10-minute period can be modeled by a Poisson distribution with mean 6. Find the probability that in a given 10-minute period, exactly 8 cars will enter the safari park. So again, this is our basic question where we are saying x belongs to the Poisson, and it is 6, so that we are px equals 8 is equal e to the minus 6, 6 to the 8 over 8 factorial, which is 0.103. Decimal point there. So that would be part A. Part B states find the smallest value of n such that the probability that at least n cars enter the safari park in that 10-minute interval is less than 0.05. So find the smallest value n such probability that at least, well, if at least n cars are entering, it's going to be x is greater than or equal to n. Now, you can remember how we would do this beforehand. We could write this as equal to 0.05, or we could flip it on itself and say, well, the probability of x being less than n is equal to 1 minus 0.05. So the probability that x less than n is equal to 0.95. So what we need to then look at, we have our lambda as 6. So what we need to look down here is where is the first place where we have it less than 0.95. Remembering, okay, so let's if we try a couple, if we say 10 here, so the probability of x being less than 10 is equal to the probability that x is less than or equal to 9, and x is 0.9161. Well, that's not the same value as 0.95. Even though you put the inequalities in, it should be obviously is less than 0.95. So if this is less than, so it needs to be greater than here. I should have put that in at the start, but it is, if I change that to there, and needs to be greater than, needs to be greater than 0.95. So as you can see, this is 0.916. So then probability that x is less than 11 is equal to the probability that x is less than or equal to 10. If we find 10 here that is 0.9574, which is correct, meaning that n is equal to 11 as our answer. Then it goes on, the probability that no cars enter the safari park in m minutes, where m is an integer less than 0.05. Again, find the smallest value of m. So if we have a look at the top here, we were given the mean value in a 10-minute interval. So we want to find the number of m minutes. So we need to work out what is this in terms of minutes. Well, we would put, if it's 6 in 10 minutes, so 6 in 10 minutes, it's got to be 0.6 in 1 minute. So we're going to say y belongs to a Poisson distribution of 0.6 m. And we now need to find the smallest value of m. Well, if we look back at our equation and we say, if we put in the probability that x is equal to 0, using the formula, you can say e to the minus lambda, where lambda is 0.6 m, times lambda to the power of 0 over 0 factorial. Well, this is equal to 1, this is equal to 1. So what we end up having is e to the minus lambda must be the smallest value of, find the probability in integer less than 0.05, put that minus there. So it's less than 0.05. If I sort of, have I got enough room? Yes, I think I have got enough room. If I sort of put a line down here, we basically need to solve that. How you would solve it is you can straight away take logs of both sides, L natural log, so that we can get minus lambda. Or what I would prefer to do, because e to the minus lambda is the same as 1 over e to the lambda, and that is less than 0.05. If I then rearrange things, bring that up, bring that down, we would have e to the lambda must be greater than, because that's down here, 1 over 0.05. Take ln of both sides. We would have lambda must be greater than ln of 1 over 0.05, which must be greater than 2.99. And if I square this off here, so that we would say that 0.6 m, therefore 0.6 m is equal to 2 greater than that. So we're going to say 3 m is equal to 3 divided by 0.6, which would give me 5. So we have our lambda as 3, and we have 5 as our value for m, which is the smallest value of m. The next part, which I will put in this section here, which is part D, find the probability that there is current at the safari park, find the probability that there is less than 5 minutes between the next car entering the safari park. Well, you've done all the hard work. You've worked out that your lambda is going to be 3 from before, in which case you would then do W belongs to Poisson distribution of 3, and that PW is greater than or equal to 1, which is 1 minus the probability that W is equal to 0, which is going to be 0.9502. I'll put a decimal point on there. And then that's your answer. Going on to the next question. Should give myself a little bit more space, and the fact that this is down here, but you'll be able to see because I'm only needing for 1, okay, for when the Poisson is equal to 1. So again, this is a similar question as before. So if you want to pause it, try it, and then work your way through. I'll try and sort of put more space in between each one. So here we have members of a conservation group record the number of sightings of a rare animal. The number of sightings follow Poisson distribution with a rate of 1 every 2 months. Find the smallest value of n such that the probability that there is at least n sightings in 2 months is less than 0.05. Again, they seem to like the 0.05. I think it's because of the fact that it comes up with 2.99 as we've done previously. And then you can either say it's greater than, which it would be 3, and then it makes a nice whole number. So find the probability, as we said. So we have x belongs to the Poisson of 1. And that we're saying that px is greater than or equal to n is find the smallest value such that n sightings is less than, I'll put the inequalities in straight away this time, 0.05. So we're saying that we must have probability of x being less than n is equal, not equal to, is greater than 0.95, 1 minus the above. And then if we have a look at our 1 down here, we're looking for the first place when it is greater than 0.95. So if we say the probability of x being less than 4 is the same as the probability of x being less than or equal to 3, which gives us a value of 0.981, 0.9810, which is the first place where it is above. We're then going to say that n is equal to 4 for that first question. Part B, so this is part A. Part B says, find the smallest number of months m such that the probability of no sightings in m months is less than 0.05. Again, it's very similar to the one we've done previously. So if we had 1 every month, here we're going to say that y belongs to the of m over 2. That 2 is a bit dodgy. There you go. Here we're going to use the formula again for px equal to 0, so that we would have e to the minus lambda less than 0.05. Rearranging it again, we would have e to the lambda greater than 1 over 0.05. Take logs of both sides, natural log. Try not to hide that in the way, so that you end up with lambda must be greater than 2.99. Therefore, lambda is equal to 3. So that you have, to work out m, it's m over 2 is equal to 3. Therefore, m is equal to 6. For part C then, if I put a line down here, part C, find the probability that there is at least 1 sighting per month in each of 3 consecutive months. So here we're going to have W belongs to the Poisson of 0.5, because here we're looking at 1 sighting per month, and here was 1 every 2 months, so it's 0.5 per month. Got to be careful with that. And we're going to say that the probability, how many do we want? At least 1 sighting per month. So PW is greater than or equal to 1. And because it is for 3 consecutive months, we're just going to cube that. To work out probability of W is greater than or equal to 0, as it greater than or equal to 1, we would then put 1 minus the probability of W equal to 0 cubed, which is equal to 1 minus 0.6065 cubed, which gives us an answer of 0.0609. And then for part D, should have enough room here, find the probability that the number of sightings in an 8-month period is equal to the expected number of sightings for that period. Well, in an 8-month period, if we had one every 2 months, then for an 8-month period, we would expect to see 4. So expected is 4. So what's the probability? Expected sight of that period is equal to 4. Therefore, if we say t belongs to of 4, and then we put down t equals 4, we can, as you said, you can calculate it by the way, but it's going to be 0.1953. That is a 5. Actually, let me just rub that 5 out. There you go. And there's that answer to that one. Moving on to question 8. Sorry, not question 8, question 7. So here we have, it is given that y belongs to the Poisson lambda, where lambda does not equal 0, and that we have the probability of y equal to 4 is equal to probability y equals 5. Write down the equation for lambda, hence find the value for lambda and the corresponding values for p equals y equals 5. Sorry about the equal sign on terms of these. These are equals here. I'm hoping you can see it better. So again, we have our distribution y belongs to the Poisson lambda. This time we haven't been told what lambda is, but we have been told that the probability that y equals 4 is equal to the probability that y is equal to 5. If we were then to write out the equation, as it's asked us to do, we would say that e to the minus lambda, and then it would be lambda to the power of 4 over 4 factorial, and that was equal to e to the minus lambda, lambda to the power of 5 over 5 factorial. What I'm hoping you can see straight away is that these would cancel with each other, and that you would rearrange it so that you would have 5 factorial over 4 factorial equal to lambda to the power of 5 over lambda to the power of 4. That 5 looks too much like a 6. To the power of 5. So that's simplifying this down, you would then have 5 factorial, sorry, 5 times 4 factorial over 4 factorial, so that they would cancel, is equal to lambda. Therefore, lambda is equal to 5. And then working out that lambda is equal to 5 when we have py equals 5 would simply be e to the power of minus 5 times 5 to the 5 over 5 factorial, and would give you a value of 0.175. I'll go back to black, I think. Moving on. So nice question, that one. There is one further along that you might want to sort of have a look at, and it'll show you how it differs slightly. Next question. So here we have, in a rock, small crystal formations occur at a constant average rate of 3.2 per cubic meter. State a further assumption needed to model the number of crystals formations in a fixed volume of rock by a Poisson distribution. So again, let's relate it to the context of the question. So part 1, we're going to say crystals must occur independently of one another. For the first part. Here, in the remainder of this question, you should assume the Poisson model is appropriate. So calculate the probability that in 1 cubic meter of rock there are exactly 5 crystals. So again, notice the word calculate, so that we are saying that we are x belongs to a Poisson distribution of 3.2. And then calculate probability in 1 cubic meter. So let's have a look. 3.2 per cubic meter, so that's fine. They're exactly 5, so it's going to be px equals 5 e to the minus 3.2 times 3.2 to the power of 5 over 5 factorial, and that is equal to 0.114. That's part 2. Part 3, calculate the probability that in 0.74 cubic meters of rock there are at least 3 crystal formations. So here we're going to put it as y belongs to the Poisson, and this time we're going to do 3.2 times 0.74 because our average has changed. So then this is going to be 2.368. And we're asked to work out the probability of x being greater than or equal to 3, because it's saying that at least 3 formations, which is the same as 1 minus the probability of x, not x, it is y. Sorry. So we have y and we have y being less than or equal to 2, which is, again, calculator or tables 0.57809, which is equal to 0.4219. Moving on, again, we need the tables for the next 2 calculations, so I've put them in. So cars arrive at a random at a toll bridge at a mean rate of 15 per hour. Explain briefly why the Poisson distribution could be used to model the number of cars arriving in a particular time interval. Notice it's with 1, so A, it's giving you all the information here, it's random and it's got a mean rate, so I would put both of them in. Cars arrive at a toll bridge independently at a constant mean rate. Part B. Phil stands at the bridge for 20 minutes. Notice 20 minutes. This is 15 per hour. Determine the probability that he sees exactly 6 cars. So our lander, we're going to say that x belongs to well, if that's 15 per hour, 20 minutes, so it's going to be 15 divided by 3. So it belongs to 5, because obviously 20 minutes is a third of an hour. And then we want to see exactly 6 cars. So px equal to 6 is e to the minus 5 times 5 to the 6 over 6 factorial, which is going to give a 0.146. And then part C, where we need the tables for. Using the statistical tables provided, find the time interval in minutes for which the probability of more than 10 cars arriving is approximately 0.3. So the probability of x being greater than 10 is approximately 0.3, which would mean that the probability of x being less than or equal to 10 is approximately equal to 0.7. So we would look at 10 on our tables here, and we would find as close as possible to 0.7, because obviously that is going to be 1 minus 0.3. Don't it to be, if it's greater than 10, then it needs to be less than or equal to 10 for this. So for lambda to be 6 is 0.9, 0.9 for 6.5, 0.9, 0.86, 0.81, 0.76, getting closer. There you have it, 0.7060. So that's approximately equal, because the next one is 0.64. So there's 6 away on this side. Therefore, from our table, then you can say that lambda is equal to 9. So you know that the average is 9, and we want to know how many, what the time interval for that is. Well, we would simply do, if it's 15 per hour, we would do 9/15 times 60, which is equal to 36 minutes. So you would expect an average of 9 per 36 minutes. Next question. So again, we need the tables sort of attached to here. Cars arrive at a car wash in such a way that a number arriving during an interval of length t minutes has a Poisson distribution with mean 0.25t. Find the probability exactly 4 cars arrive between these times, so it's 15 minutes. So that we would say that x belongs to a Poisson of 0.25 times 15, which is 3.75. And the first question is exactly 4 cars, so px equals 4 is, I'm just going to write down the value, 0.194. You know how to calculate it by now. Part 2, more than 6 cars arrive between. So for part A1 and part A2, more than 6 cars arrive between that. So that's 20 minutes. So we're going to say that y belongs to, and then it's going to be 0.25 times 20, which is equal to 5. And it's asking us for more than 6 cars, so the probability of x being greater than 6 is 1 minus the probability of x being less than or equal to 6. And again, we know how to calculate this, so I'm just going to put down the answer, 0.2378. And then part B is find the probability that less than 10 cars, so the probability of x being less than 10 is the same as the probability of x being less than or equal to 9 for our tables, is equal to 0.7166. 0.7166. So here we're looking at 9 and finding 0.7166 to find lambda. So from our tables 7166, we have this here. So therefore lambda is equal to 8. And if we have, then we need to find out the value of t. Then we have 0.25t equals 8. So t is equal to 8 times 4, which is 32. The last question then on the other side is the number of letters X arriving each morning at a house may be modeled by a Poisson distribution with mean 5, determine the probability on a random chosen day. The number of letters arriving is equal to 2 and more than 3. It's part B that I really am interested in, so I'm just going to put the answers to A and 1. So we have again X belongs to the Poisson of 5. That's a hideous 5. So equal to 2x equal to 2 is 0.084. And then it was the probability more than 3. So for part 2, x being more than 3 is equal to 1 minus the probability x is less than or equal to 3 from the tables, and then that is equal to 0.735. So part B, it says the number of letters Y arriving each morning in the house is recorded by a Poisson distribution of, we've got mu now. Given that is the case, determine the values of mu. So we know that Y belongs to Poisson mu, and probability of Y equal to 2 is equal to Y equal to 0 or Y equal to 1. Notice the or. So we would then have mu e to the minus mu times mu squared over 2 factorial equals, I'm going to take e to the minus mu outside. For 0, it's just going to be 1, and then it's going to be or, which is plus, and then for 1, it's going to be mu to the power of 1 over 1. And again, I hope you can see that they cancel with each other, so that you have mu squared equals 2, because it's taken 2 over the side, plus 2 mu. So then we have mu squared minus 2 mu minus 2 equal to 0. And using the quadratic formula, I would expect to see 2 plus or minus, or mu equals 2 plus or minus the square root of 12 over 2. So mu is equal to 1 plus or minus 3. You can only have one, well, 1 minus root 3 is a negative number, no good. So mu is equal to 1 plus root 3, which gives an answer of 2.73. I'd like to thank you very much for listening to this video, and if there are sort of any more videos that will need your help with maths or any other subjects, then please visit the website, and you can see that there are several videos there to help you with your sort of revision. Thank you very much.